So, so we work over a finite ring, and in fact, in the general situation of a finite commutative ring with a 1, and examples of these are finite fields, the integers modulo m, and also rings of the form. You take a finite field, so integers modulo p, and you add, for example, a primitive fourth root of unity or a primitive cube root of unity, and so this gives you interesting situations for coding theory. And so if you are not super familiar with rings, you can always think of the situation of FQ, because what I will say will also be, there will also be some new results over FQ. So if you work, however, in the generality of a finite commutative ring, then you can write it as a product, a finite product of finite local rings. And the local ring is just a ring which has exactly one maximal ideal. So for example, a field is a local ring because it has only the zero ideal. The integer modulo 8 or modulo a power of a prime in the same way only have a maximal ideal because the only ideal, the largest ideal is the ideal generated by the prime. So for example, for the integers modulo 8, the maximal ideal is the ideal generated by 2, because that contains every other ideal of this ring. And of course, there are also rings of interest which are not local. For example, the integers modulo 6, which have two maximal ideals generated by 2 and 3. However, as I said, every finite commutative ring is a product of local finite local rings. And for example, for z modulo 6, this is the product of the integers modulo 2 and the integers modulo 3. And so, as the Chinese remainder theorem says, in the special case of the integers modulo m, you can write that as a product of quotients of z by powers of primes. And this gives you the decomposition. So this is an example of this decomposition that you see here. Okay. And then we will be looking throughout the talk, we will need to look at the special ideal, which is called the Jacobson radical of the ring. And this ideal is just the product of the maximal ideals of each of the local rings. Okay, so in the case of the integers modulo m, this Jacobson radical is the ideal generated by the products of all the primes that divide m with exponent 1. And so, for example, in the special case that m is a product of distinct primes, or when we are looking at the finite field, for example, then j is 0. Okay. So, and we will be looking at support for codes. So what do I mean by support? So we work in n to the u. So our supports will take values which are in the natural numbers to the power u. So they're vectors of natural numbers. And this is a lattice with the usual partial order given by comparing two vectors coordinate-wise. So a vector s is less than or equal than a vector t if and only if each of its coordinates is less than or equal to the corresponding coordinate of t. And as I said, this is a partial order, it's not a total order, so not all pairs of vectors are comparable. But one thing you can always do is you can take the join of two vectors, and that is the least vector, which is larger than or equal s and t. And so in practice, you can write it as the vector whose ith coordinate is the maximum of the ith coordinates of s and t. So for example, if you want to do the join of 0, 2 and 3, 1, then this will be the vector 3, which is the maximum of 0 and 3, and 2, which is the maximum of 2 and 1. Okay. And now we will define a support to be a function that takes a vector in R to the n. So this will be where our code words will live, and associates an element of n to the u. And we ask for support to have the following properties that remember the ring structure and the module structure that we work with in this case. So Well, the first property is very natural. It asks that the support is 0 if and only if the vector is 0. And then, as I said, we want to have a compatibility with the operations of the ring. So we want that when we multiply a vector v by a scalar r in the ring, then the support becomes less than or equal. And we also want that the support of the sum of two vectors is at most the join of their supports. And these latter two properties make it so that when you take a vector which is in the module generated by v and w, then its support is at most the join of the support of v and of w. And then we have an additional property that we will be looking at throughout the talk, and that's a property of a support, which we call modularity. We call it modularity because, again, it is connected to the module structure of R to the n, which is an R module. And it is like a cancellation property, if you want. And it can be stated like this. If you have two supports, and one of them is less than or equal than the other in one coordinate I, then you can make a combination of the two vectors where the ith coordinate of the support is 0. So it's kind of like you can eliminate the ith component of the support. Okay, so one example of support, the one that we're all familiar with, I guess, is the Hamming support, which I write here for a ring. The Hamming support, so the Hamming support of a vector is a vector of length n, which has 0 in the position where the vector is 0 and 1 in the other positions. So this is a support according to our definition, and it is also modular. Sorry, I wrote R here, but it is modular if R is a field, okay? So in the case which is familiar to us of linear block codes, the Hamming support is a support which is also modular. And usually we will also, sometimes we think of a support as a vector of 0, 1. Sometimes we think of a support as a subset of the coordinates. In the case of the Hamming support, a set of coordinates in which the vector is non-zero. So I will maybe sometimes switch between these two definitions, and I hope there is no confusion. If there are questions also during the talk, you're welcome to ask, and if I see them in the chat, I will do my best to reply. Okay. So this is our supports, and I want to make a couple of examples. So an example of a modular support over a ring, over the ring of integers modulo 4 is the following. So we can start from associating a weight to each element of the integers modulo 4. And so we assign weight 0 to 0, weight 1 to 2, and weight 2 to 1 and 3. And the reason we define it like that is because we want to capture here the property that 1 and 3 generate more than 2. And so they will have higher weight. And so now once we define the weight like this, we can define a support in a natural way by taking the vector whose entries are the weights of the coordinates of our code word. So this is a modular support. An example of a support which is not modular is the Hamming support over a ring which is not a field. So in particular, over the integers modulo 4, the Hamming support is not modular because the vector 1, 0 has support 1, 0, the vector 2, 2 has support 1, 1. However, I cannot make a combination of 1, 0 plus some element in the ring times 2, 2, which is 0 in the first component. And the reason why I cannot do that, again, is because there is no multiple of 2 which is equal to 1, because 1 generates more than 2. So the support is not modular. An example of something which we sometimes call a support and which is not a support according to our setup is the one which is naturally induced by the Lie weight. So the Lie weight is a weight on the integers modulo 4, which is 0 on 0. It is 1 on 1 and 3, and it is 2 on 2. And so again, he has this problem. I mean, its pathologies come from the fact that 2 has larger weight than 1, but it generates less than 1. And so, for example, you can easily see that the support induced by this Lie weight for the vector 1 and all zeros is the vector 1 and all zeros, and the support of the vector 2 and all zeros is 2, which is the weight of 2 and all zeros. And there is no, the 2, 0, 0, 0 is not less than or equal than 1, 0, 0, 0. However, this vector here is a multiple of that vector. So this was one of the properties that we required for support. Remember that if you have a vector v and you multiply it by r, its support becomes less than or equal. So this is not a support according to our setup. And by this, I don't mean to say that it's not interesting to look at this weight, this support. I just want to say that the kind of results they will prove in this talk, they are all blatantly false for the support induced by the Lie weight. Okay, so now once we have this support, we can associate in a very natural way a weight function and a distance function. So the weight of a vector, we can just define it as the size of its support. So the sum of the entries in its support. And now we have, once we have a weight, we have a distance. In the usual way, we define the distance of two vectors to be the weight of their difference. And one again can prove that these are indeed a weight and a distance function. And so again, as I announced at the beginning, we will be looking at linear codes over a ring. So a linear code over a ring is an R submodule of R to the n. And R submodule means, I mean, I'm sure everyone knows this, but I just wanted to stress it to make sure we're on the same page. So an R submodule is a subset which is closed with respect to sum and multiplication by elements of R. Okay, so, and now once we have a distance, we can define a minimum distance. And in the usual way, as the minimum of distances of pairwise distinct code words. And it turns out that this minimum distance, in the way we set things up, is the weight, the least weight of a non-zero code word, as we're used to from the linear block codes Hamming weight. Okay, and last definition, now that we have weights, distances, and supports in this very general setting, we can also define the support of a code as the join of the support of all the code words. Now here, our setting is finite, so we're doing a join of a finite set, so this always makes sense. But in fact, you can also prove that this is the join of the supports of a set of generators of your code. And this is handy. This is handy in case you want to compute supports. And this is, for example, again, one of our Hamming examples will be the Hamming support. So if you take your R to be a finite field and your sigma to be the Hamming support, then the support of a code is the set of coordinates between 1 and n, if the code is in FQ to the n, where there is at least one code word which has a non-zero entry in that position. So it's the usual intuitive definition of support. And I want to stress here again that although, so that our definition of support makes this equality be true. So it makes the property that the support of a code is the join of the support of a system of generators be true. However, this is not true in general for things that are not supports according to our definition. So for example, for the support, and I'm saying it in quote here because the support is not a support according to our definition, the one induced by the Lie weight, then this property is false. So if you take the support of even a code generated by one code word only, and you take its support, there could be elements in the module generated that have larger support. Sorry, this should also be sigma L. Okay, the sigma of the Lie weight. Okay, so this is now the support of a code, and once we have supports, we can define generalized weights. So generalized weights are invariants of linear codes, and they were first defined by Way in the following way. So there is one generalized weight. So we take a C, which is a linear subcode of FQ to the N, Hamming support, Hamming distance. And then for each I between 1 and the dimension of the code, we let the ith generalized weight be the minimum support of a subcode which has dimension at least I. So these are code invariants. Code invariants are interesting just because I think invariants are, I mean, it's very natural to consider invariants in all fields of mathematics, as they give you a sort of a compact way to codify some information about your objects. And in coding theory, for example, they may be useful for distinguishing codes that are non-equivalent. If you have two codes and they have an invariant which is not the same, then they're not equivalent. And these generalized weights are you know, the obvious invariants of a linear block code are the length, the dimension, and the minimum distance. And then you can define some other invariants which are a little bit less trivial to define, like the generalized weights, or you can look at weight distribution, etc. There are others as well. Okay, and the reason why Way define these invariants is because they measure security drops for linear coding schemes in a wiretap channel. And we will not get into this further, but he had a motivation also coming from the applications when he defined these invariants. Okay, and in his paper where he defined these invariants, he proved some results. For example, he proved monotonicity of the generalized weights, by which I mean he proved that the first weight is the minimum distance. The last weight is the cardinality of the support of the code, and so it's at most n, at most the number of coordinates. And then he proved that the sequence of weights is a strictly increasing sequence of integers. And this gives you immediately this second result, which sometimes people call generalized singleton bound, because it's a bound. If you look at this right-hand side, this is a bound that relates the ith generalized weight with the dimension of the code I and n. And if you take I equal to 1, then you have the usual singleton bound here. Okay, so now what we want to do is we want to define generalized weights. So now that we have support, we want to define generalized weights in this general setting of codes over rings. And so I recall that we can write our R as the product of R1 up to RL, where the Ri are local rings. And so now we can write also R to the N as a product in the same way. And this gives us a way to write C as a product of codes where each one of them is a code over a local ring. And so now when we look at codes, we will look at minimal systems of generators. So a minimal system of generators is a system of generator which is minimal with respect to inclusion. That means if you remove one of the generators, you no longer generate the code. And so if you have a field, minimal system of generators are the basis. If you are over a ring, things get a little trickier. So for example, if you are over zeta modulo 6 squared, then you can look at the code generated by the vector of entries 2 and 3. And now this 2, 3 is a minimal system of generators, obviously, because yeah, you cannot remove it, otherwise you have lost all the generators. So it's minimal. Of course, if I take 2, 3, and then I take 2, 3 multiplied by 4, which gives me 2, 0, this is again a system of generators, which is non-minimal because I could remove the second one, and I would still have a system of generators. But now what I can do is I could take 2, 0 and 2, 3 minus 2, 0, which is 0, 3. And now these two are again a system of generators for my code, and they are minimal because I think it's clear that they're minimal, because if you remove one of them, you are stuck with a subcode where one coordinate is identical to 0. And so that's not the whole code. Okay, so this shows us that if you go over a ring, the situation becomes quite a bit more complicated already, because you can have minimal systems of generators of different cardinalities. However, if you are over a local ring, and this is the interest of why I want to write my code in this way, if you have a local ring, then every minimal system of generators has the same cardinality, which I call mu of Ci. This is an invariant of Ci, which would correspond to the dimension if you were over a field. And now it is not too difficult to prove that if you are over a ring, the cardinality of a minimal system of generators of a module or of a code C is at most the sum of the mu's of its components when I write it as a product of codes over local rings. So we don't know exactly how many minimal generators our code has, and in fact different systems of generators could have different cardinalities, but we know that the cardinality of a minimal system of generators is no greater than this number, which I called big M of C. And so now that will tell me how many generalized weights I can define. So now we define generalized weights similarly to how Way defined them in the following way. So the I generalized weights is the minimum size of a support of a subcode that has at least I minimal generators. And now with this definition, it makes sense to define them for I between 1 and the largest cardinality of a minimal system of generators of C, which is this number M of C. And again, I stress that if you take a finite field and you take a linear code with the Hamming weight, this gives you the usual generalized weight defined by Way. So this is a generalization of its definition. And one can prove that if sigma is a support with this definition, then you still have that the first generalized weight is the minimum distance of the code. Whoop, sorry. And this is false if you don't have a support in general. A support, again, according to our definition, because, for example, if you take the natural support induced by the Lie weight, then you can see that the minimum distance of the integers modulo 4 squared is 1, because you have vectors of weight 1, for example, 1, 0. However, it's not hard to show, but maybe it takes 1 minute of thinking, and I will not do it here. It's not hard to show, however, that the weight, the support of any one dimension, every submodule generated by one element has size at least 2. And so now D1 is 2 and the minimum distance is 1, so they are not the same. So this property is not true for something that does not satisfy, I mean, in general, some function that does not satisfy a definition of support function. So very important in this theory are the code words of minimal support. So if you, from now on, I will concentrate on modular supports, because these are the supports for which our theory works well, yeah, it will make my life easier in terms of stating results. So once you have a support, a modular support in particular, you can define minimal code words in your code as the code word whose support is minimal. Among the non-zero elements, of course, the support of 0 is 0, and you never want to look at that, and all the rest, you take the minimal elements. And one first result we're able to prove is that if you have two minimal code words, they that have the same support, then they differ by an invertible element. So in a sense, the support identifies the minimal coord that it corresponds to. And another thing that we're able to prove is that if you have a code in R to the n, then it is generated by its minimal coord if and only if it is annihilated by the Jacobson radical, where I remind you the Jacobson radical was the product of all the maximal ideals once you wrote your R as a product of local rings. So this result has, if you think of what this means when you take R to be a finite field, then you get that J is 0, and so JC is always 0, and so you get the result that a code inside FQ to the n is generated by its minimal coords. And this generalizes a result of Asikmin and Barg, who proved that this is the case for linear block codes with a Hamming weight, Hamming support. Okay, and this result is also true and easy to prove for the Hamming support, obviously. Okay, so now we have a definition of generalized weight, and using minimal coords, we embarked in a study of the properties of this generalized weight. And one thing which we were able to prove is that the ith generalized weight is the size of the support of a code inside C, which is minimally generated by I minimal coords, so by I coords of minimal support. And we were also able to prove results along the same lines. So we generalized the results of Way. So we were able to prove a monotonicity result on the generalized weights, and a generalized singleton bound, which, as I mentioned before, follows directly from a result of the first kind, the monotonicity result. And here, there's this number here that maybe I don't want to get too much into what this represents, but just think of it like this. Given a ring and given a support, this is a number which you have, and that tells you what is the largest possible value for a generalized weight. In the case of R equal to FQ and sigma equal to Hamming support, this is n, the number of coordinates. Okay, so many properties of many invariants of a code can be computed starting from the matroid associated to the code. And so I want to say a few words starting from the case of, again, a linear block code and Hamming support. So if you have a linear code, you can associate a matroid in the following way. So if you don't know what is a matroid, I guess you will take this as the definition. So a matroid is given by an information of a ground set and a set of subsets of it, which are called, in this case, there's many ways to give a matroid, and I will give the so-called dependent sets. So for us, the ground set is 1n, the set of here coordinates, and the dependent sets will be the set of indexes that correspond to the columns in the parity check matrix of C, which are linearly dependent. So in other words, the dependent sets are sets which contain some support of some non-zero coord. So a matroid is studied, matroids are object of independent interest, which are studied in combinatorics. And in the case of a linear code, it has been showed that the matroid determines many of the invariants of the code. And I mean, if you listen to the talk of Relinde and of Heide, which I unfortunately missed, but I think it was going in this direction yesterday, you have heard of results that are connected to this in a different setting, but along the same lines. Okay, and if you like, as I do commutative algebra, you can also think of a matroid as an equivalent information. You can think of it as an ideal. So To each matroid, you can associate a Stanley Reisner ideal, which is an ideal generated by monomials, and these monomials correspond exactly to the dependent sets of the matroid. So each monomial generator of this Stanley Reisner ideal is a product of variables indexed by the elements of some dependent set. And you just choose a field and you write down this ideal, and this is called the Stanley Reisner ideal of the matroid. Okay, so we are coming to, I'm building up to our main result here. So for linear codes with the Hamming support, you can compute generalized weight using the associated matroid in the following way. And I have an example here because maybe sometimes an example explains more than 1,000 words. So if I take the even weight code, then it's parity check matrix is the row of all ones of size 1 by n. And then the dependent sets here are all sets of cardinality 2, and then all the sets of larger cardinality as well, obviously. And so here you can write this as in the following way. If you write the ideal, you will take all the degree 2 monomials, which are the product of xi, xj for I and j distinct. And so this is the square free, all the square free monomials of degree 2. Okay, so this is the matroid of this code, and this is the Stanley Reisner ideal. And it's also easy to compute in this case because this is a simple code where we understand everything. It's easy to compute the generalized weights, and the ith generalized weight here is I plus 1 for all I. And Johnson and Verdour have proven that if you compute the minimum free resolution of this ideal, then this determines the generalized weights in the following way. So I don't want to get too much in what minimum free resolutions are, because I think if you have never seen them, maybe yeah, it's not something that I can explain in 1 minute, but just let me give it a shot. Okay, so you have an ideal, and this ideal is generated by some monomials, and so you can write a surjective map where you send, if you have t monomials, you send you take s to the power t, s is the polynomial ring, and you send the standard basis of s to the t, each element to one of the monomial generators. And here I will put some numbers which remind me of what are the degrees of the monomials. So this is a surjective map, and I can compute its kernel. And once I have its kernel, I can compute a minimal system of generators of it, and I can make another surjective map from a free module to the kernel. And so this gives me a an exact sequence of free modules, where these numbers, which are called the graded Betti numbers, remind me of what were the degrees of the generators that appeared at each step. And so now it's possible to prove. Actually, Hilbert has proved that this process ends, and so you get a finite exact sequence, an exact sequence of finite length. And so if you had the even weight code in F2 to the 4, this is my attempt at making this digestible for someone who's not super familiar with these concepts. So there are 6 monomials of degree 2 in 4 variables. So the first map will be 6 copies of S in degree 2. And now I can compute the kernel of this map. And now I wrote here a set of generators of this kernel. For example, if I look at these 2 monomials, if I multiply this one by x3 and this one by minus x2, and I make the sum and I get 0. So this vector is in the kernel. And now you have to believe me that these are the generators of the kernel. In the monomial case, this is all very well understood and easy to compute. And so now these have entries of degree 1. So here I put a 3, which is 2 plus 1. And I keep going like this, and this stops after 3 steps. Okay, so this is called the minimum free resolution of this ideal here of the even weight code. And once again, Verdour and Johnson and Verdour proved that these numbers tell you what the generalized weights are. And in fact, look here. So here 2 tells you that the minimum distance is 2, 3 tells you that T2 is equal to 3, and 4 tells you that D3 is equal to 2. And the fact that this has three steps tells you that the dimension of the code is 3. Okay. So now we ask ourselves, maybe sometimes we can compute the generalized weights via matroids, but obviously you only have a chance to do that if your support takes values in the set 0, 1 to the u, because a matroid is a set of subsets. So it's a set, it corresponds to vectors that have entries only 0 and 1. So in that case, we proved that in our setup of a modular support, then you associate, so the dependent sets defined as sets which contain the support of some vector for the support that you have chosen, give you a matroid. So there is a matroid there, which is floating around and that you could look at, okay? And as I said, in general, you cannot do this because it just doesn't make sense. But what you can always do is you can associate monomials, because for monomials, you don't necessarily need to take a product of variables. You can take a product of variables to higher powers as well. And so this was our idea, to extend this beyond the supports which take value in 0, 1 only. And so we associate to a code a monomial ideal, which is generated by monomials which remember what are the minimal supports of the code. And for example, okay, for example, if I don't know, the support of an element of the form 1, 1x is 0, 1, 2x, then to 1, 1, 0, I will associate the monomial x2 for this one, x2, x0, x1 to the 0, x2 to the 1, x3 squared. And so now with this setup, we can prove the following result, which is the main result in our upcoming paper. And it says that once you take your code and you have a modular support over a ring, then you can associate this monomial ideal, and the minimum resolution of the monomial ideal tells you what are the generalized weights of the code. And more precisely, the length of this resolution tells you this number of MC, largest cardinality of a minimum generating set of C. And the smallest of these numbers that we read in each step of the resolution will tell you what is the generalized weight in that step. So in fact, the resolution contains more invariants than just the generalized weights. Yeah? So for example, we had in the previous example a code for which, okay, I didn't explain the example so truly, so maybe I shouldn't get too much into detail in this, but we have a code, we associate somehow via a support, we associate this ideal, we write down the resolution, and now we have the dimension, okay, which we had, obviously, it was easy. We have the minimum weight and the D2 as well. Looking at this, we take the minimum here of 3, 4, 5, which is 3, and here 6. Okay, so this was our main result, and now I just want to say one final word on the situation of supports which are not modular. So if you take a support which is not modular, our main theorem is false. And for example, a very simple example, I could assign to the vector 1, 0 support 1, 1, and to the vector 0, 1 support 0, 1, and to 1, 1 support 1, 1, this over f2 squared. And it's easy to prove. It has to be checked, but it's easy that this is a support and it is not modular. And now if you look at the elements of minimal support in F2 squared, you see there's only one and it's 0, 1, and its support is 0, 1. So the only element you put in the ideal here would be y. So now you have the ideal generated by y, and if you resolve it, the resolution doesn't even have the right length, and therefore it's very far from giving you the generalized weights. Okay, and so to summarize, in this work, we have worked with linear codes over a finite commutative ring, and we have given a general definition of support and showed that the support induces all the usual setup for codes, so weight, distance, generalized weights. And we identified a family of supports, which are the modular supports, which are very nice properties and allow us to extend a lot of results that are true for the Hamming support to this much more general setting. And we also showed how to associate a monomial ideal to a code. And this ideal plays the role of the matroid when the matroid does not exist. And the algebraic invariants of the monomial ideal determine the generalized widths of the code. So this is all I wanted to say. Thank you for your attention.